This video is a review of the properties of exponents and logarithms. So we'll start with the most important number for exponents, and that is the number e. So the number e, numerically, it's an irrational number, but we can approximate it as 2.71828 ... and it continues from there. Typically 4 to 5 sig figs is going to be good enough for us and our purposes and undergraduate PChem homework sets and exams and the like. So the function e to the x, which we would say as e to the x, is going to show up everywhere in PChem. So you will never be able to get away from e to the x or e to the minus x squared. It's going to follow you around everywhere. And for good reason. It's a very useful function. Okay, so what about, we have e times e, that would be e squared. So numerically, that would be something around 8, but typically exponents are convenient to just keep expressing in this form. If we have e times e times e is, of course, e cubed. So exponentiation is repeated multiplication. We can remind ourselves. So the number of times you multiply something times itself is going to be the exponent that you take it to, at least for integer exponents. So we have pi of I equals 1 to n of e equals e to the x. So this symbol here, pi, is when you're multiplying things together. So a sigma is when you're summing things together. Pi is when you're multiplying things together, a product. Pi and product both start with P, sum and sigma both start with S. So from I equals 1 to n, so you're multiplying e times itself n times. That's going to be e to the n, not e to the x, e to the n. So that works for any integer power, and that makes sense. But we can do this for even non-integer powers as well, and it provides some very useful properties for us. So we are going to say some general rules for exponentiation, and this works for other numbers as well. This could be 2 to the n times 2 to the n. This could be pi, it could be 8, could be 4.23. Any number in general holds for most of these properties that I'm mentioning here for exponentiation, but since we use e so much, I'm going to use that one as the example. So multiplying two numbers that are exponentiated times each other gives you a sum of those exponents. So if you multiplied e times itself n times and then multiplied e times itself m times, that would be n plus m times. So that'll make sense. If we have e to the n divided by e to the m, that is equal to e to the n minus m. So you multiplied it times itself n times, and then you divided it by itself m times, so you have n minus m times as your net result. All right, we have 1 over e to the n equals e to the minus n. So that's like dividing it by itself n times. E to the minus n, the inverse exponent. All right, square root of e equals e to the 1/2, as we know. So this is a very useful way to express things when you have very long terms which would be cumbersome to write a square root for. And it's also nice because in general you might not just have square roots, but you might have other more advanced roots. We might have the nth root of e, and that is e to the 1 over n. So if you take the nth root of e, whatever number you multiply times itself n times to get e, that is equal to e to the 1 over n. Because if you multiply that number together that many times, you'll get e to the 1 over n. You'll get e. Yeah, if you multiply e to the 1 over n times itself n times, you will get e. Okay, and then we have the nth root of e to the m, which is equal to e to the m divided by n. So that's the same thing as e to the 1 over n, but now on the inside, instead of e, you have e to the m. So it's e to the m divided by n. All right, special cases, as would be true for any number, e to the 0 is equal to 1. Any non-zero number to the 0 power is going to equal 1. We have 1 to the n equals 1. Taking 1 to any power is just going to give itself again. So 1 is kind of the exponential identity. You have 0 to the n is going to equal 0 as well. Multiply anything times 0, you're going to get 0 back. Multiply any finite number times 0, that is. And of course, e to the 1 is going to equal e. All right, so those are a lot of the general properties of exponents which are useful to know because there's going to be a lot of algebra involved in PChem problem sets, homework, assignments, exams, etc. So being adept at that kind of algebra and manipulation saves you not only a lot of effort, a lot of time, but a lot of getting the wrong answer where the right answer was a fairly simple manipulation of some exponents. Okay, so what about the inverse of that? So exponentiation, and then there's logarithms. So we know that 10 squared equals 100. So 10 times itself twice is 100. So we can also say that log base 10 of 100 equals 2. So the power that you need to raise 10 to get 100 is 2. That's how the logarithm function is going to work. So we know that 5 to the minus 2, well, that's going to be 1 over 5 squared. So that's 1 over 25. So the log base 5 of 1 over 25 is equal to minus 2. So in general for logarithms, we're going to have a to the x equals y. That's going to be log base a of y equals x. All right, so that's, as we said, for kind of general logarithms. They have a base and then some number and the power that you take the base to get the number. All right, so log base e of x is a special logarithm, and that is written as ln x. We remind ourselves from probably Algebra 2 that that is the natural log of x. Okay, so we say that that is the natural log of x because natural logs are logarithms to the base e. As we said, we have a lot of things that involve e to a power in chemistry and physics, so you can imagine it's going to be useful to have a lot of things of logarithms to the base e compensating for that. All right, so what are some special properties of logarithms that we can use to help make working with them easier? So the log of a times b is equal to the log of a plus the log of b. And you can check to yourself that this works using the properties of exponents if you translate it from the logarithm expression into the exponent expression. These are pretty much one-to-one mirrors of each other. Oh, should be saying ln there. Let me go ahead and say that that's ln. Don't want to be confusing in the intro. Okay, ln. All right, ln, natural log of a over b, is equal to log a minus log b. All right, that's useful as well for factoring or combining logarithms of various things. Log of a to the b is equal to b log a. I forgot to write that one over here. Let's write this one over here. So one thing that we forgot to write on this side is going to be e to the n to the m is equal to e to the n times n. So if you take e to the n times itself m times, that's going to be e to the n to the m. So that'll be e to the n times m. And that's where this rule comes from as well. Log of a to the b equals b log a. All right, and we have log of, what color am I on? Okay, let's go back here. Log of 1 over a is equal to minus log a. We can tell that up here as well. Log of 1 over b was minus log b there. All right. Next one up, a few special cases remaining. The natural log of 1 equals 0, because any number to the 0 is equal to 1. So e to the 0 is no exception. The log of 0 is equal to minus infinity. It's actually diverging by there as well. So if you take any number to the power minus infinity, you're going to get 0. Mathematicians, don't freak out on me on that one, because we're going to be doing a lot of that, playing fast and loose with the rules of infinity in this playlist. So if you're going to be a stickler for the rules of how to work with infinity, this is not going to be the playlist for you. All right, natural log of e. What power do we have to take e to get e? That's going to be 1. So that makes sense. So natural log and e are kind of natural log of x and e to the x are inverse operations. So we can similarly use e to the natural log of x is equal to x. All right, those are some general properties of logarithms and exponents that are very handy and very nice to work with. For most of these work in general for logarithms of other base rather than e, and for exponents of other base rather than e. But since natural log and e are used so frequently in chemistry and physics, that is the example that I chose to use for these cases.